In the previous lecture, we have discussed about the digital to analog signal transmission, means digitization, and this was the block diagram which was covered in the previous lecture. So any digital signal, any analog signal which is to be converted into digital requires three steps, and those three steps are sampling, quantization, and encoding. In detail, we have discussed about the sampling. Sampling is nothing but converting our analog signal into a sampled form, and this particular sampled signal is also called as pulse amplitude modulated signal. And we have also seen the block diagram for pulse amplitude modulated signal, and there we had also seen the different types of sampling such as natural sampling, impulse sampling, and flat top sampling. So sampling is the first step of converting analog signal to digital. The second step of conversion is nothing but the quantization. So in this lecture, we will discuss about the quantization, and parallelly, we will also discuss what is the encoding. So, quantization is the process of rounding off the amplitude of the flat top sample to a manageable number of level. As we know that analog signal is defined with infinite values, infinite levels, infinite values. So when we convert a analog signal into a samples, let us say we have considered flat top sample. So we have to round the quantization, we have to round the levels of the analog signal to a manageable level. The total voltage range is to be subdivided into a smaller range. For example, if a sine wave with a peak amplitude of 5 volt varies between plus 5 and minus 5, passing through every possible amplitude in between. So we are considering example for a 5 volt of sine wave, and peak amplitude is 5 volts. So there will be positive peak of plus 5 volt, negative peak of minus 5 volt. So rounding off this between the every possible value, and later on after rounding we are going to assign a PCM code. So we will understand with the help of example what is PCM code, and this particular PCM code is having an absolute magnitude, and this magnitude is called as quantizing. So the quantizing of an analog signal is done by digitizing the signal with number of quantization level, and what is quantization level that we will understand with the help of example. So quantization is representing the sampled values of amplitude by a finite set of level, which means that converting a continuous amplitude sample into a discrete time signal. So quantization is going to be a second step after the sampling, and there you are assigning a nearby voltage level to each and every sample, and that particular process is called as quantizing. So if we consider an example of an analog signal, so this is a random sine wave or the analog signal is drawn. After sampling, quantizing, the analog signal will be looking like this. So this blue line corresponds to our analog signal. The red line indicates that it is the quantized signal after sampling. And you can see on the y-axis there are codes which are assigned, and this particular code is a 4-bit code which is assigned to each and every quantized level, and therefore the red lines indicate here that this is nothing but a quantized signal having, and this particular quantized signal comes from the sample. So when you are quantizing the signal, the original signal and the quantized signal will always have some difference. So you can see here this particular signal is having some voltage here, but it is quantized to this particular code. So the original signal and the quantized signal will always have a magnitude difference between them, and this particular this particular difference, the magnitude difference between the adjacent step is called as quantization interval, or it is called as quantum. So again, looking to this particular diagram, this particular code 0101 and 0110 is having some difference in the magnitude, and this particular size, this particular level, we are calling it as a quantization interval, which is also called as quantum, and the magnitude of this particular quantum is called as resolution. So difference between this magnitude and this magnitude is called as a quantization level or a quantum, and the magnitude of the quantum means what is the size of this particular step. In the some books they are writing it as step size, so this particular size of the step is called as resolution. Now, very important point to understand, the smaller the magnitude of quantum, means smaller the resolution, the better magnitude of the quantum, the better the resolution, and the more accurately the quantized signal will resemble. So if the magnitude of this particular step size is smaller, meaning you will have more number of quantized level, and therefore the reproduction of the signal will be easy. And if your step size is larger, means you have resolution, means the magnitude is very large and therefore resolution is very poor, and in that case the recovery of the original signal becomes difficult. Remember that why we are talking about recovery, because the analog signal we are converting into digital that we are transmitting. At the receiver, we have to recover our analog signal back. And that is why, if you remember, at the time of sampling also, we have talked about recovery. So for proper recovery, you need to follow Nyquist rate. And even while quantizing also, we are talking about recovery. So if the magnitude is the smaller, resolution is smaller, then we have a quantized signal which will have the same shape of the analog signal. So here we are considering one example, and this particular example is a random signal, any random signal, which is sampled at an interval of T1, T2 and T3. So complete signal is sampled only in three interval, T1, T2 and T3, and you can see this is the sampled signal at the interval of T1, T2 and T3. On the y-axis, if you can see, the ground line is 0. It is having an amplitude of +1, +2, +3 on positive side, and -1, -2, -3 on the negative side. So this is our analog input signal and the sampling pulses. These are the sampling pulses. Now, to each and every sampling pulses, we are going to have a quantization range. So we are going to decide a quantization range. So +0 will be indicated a value of 0 volt to +0.5. +1 will have a value of 0.5 to 1.5. +2 will have a value of 1.5 to +2.5. +3 will have a value of +2.5 to 3.5. And similar way, we have a minus range also. So we are going to assign, since there are 8 levels which are, this particular decimal value is divided into 8 level. So we are going to assign a 3-bit code to it, and that 3-bit code may, the first bit is representing a sign. Wherever the positive is there, it will indicate 1. Where 0 is there, it will indicate negative. And other 2 bits are going to represent the magnitude of this. So this particular analog signal is going to be assigned with the codes, and that particular codes are summarized in this table. And these codes are going to be assigned to a decimal value, and this decimal value we have quantized in this particular range. So here you are having a sampled signal which is called as our PAM signal, and then to each and every level we are assigning this particular code, and this particular code is 110. So 110 means this particular sample we have rounded to +2 volt. 001, so you can see 001 code is here. So this particular sample we have rounded to -1 volt, and here it is 111, so 111 corresponds to +3 volt. So that particular we have rounded to +3 volt. So this is our code which is assigned. So our analog signal of this is converted into a digital and this is what is called as a pulse code modulation, and this particular 3-bit code is called as a PCM code. So when we are doing this rounding off, if you see this particular level was somewhere there at 2.6 volt, but that we have rounded this particular, see this sample is taken at 2.6 volt, but while quantizing we have rounded that to plus 3 volt because 2.6 is nearby to plus 3, so we have rounded this particular sample at plus 3. So there is always a rounding off procedure, and because of that there is a difference between your quantized signal and the original signal. So each PAM sample voltage is rounded off to the closest available level, and then it is converted to PCM code. So this particular round of errors are reproduced when the code is converted back to analog signal. So whatever this particular difference is there between the quantized level and the original signal. So for our example, this sample was at 2.6, but we have rounded to 3 volt. So this particular is called as a quantization error. So 3 minus 2.6, that particular is the quantization error. So the quality of the PAM signal, means quality of the number of samples, can be improved by using a PCM code with more number of bits, or you can reduce the magnitude of quantum and improve the resolution, or you can do a sampling at a faster rate. So if the sampling is done at a faster rate, or the step size is reduced, or you are representing a sample with more number of bit, you can always improve the quality of this PAM signal, and therefore you can have more number of samples, and therefore the reconstruction of the signal becomes easier. So the quantization is nothing but process of assigning a nearby values or a nearby levels to the original signal, and therefore quantizing that particular signal. And the third step is encoding to each and every quantized level. We are going to assign a code. So we have taken an example of 3-bit code. It can be 4-bit, it can be 2-bit, it can be 8-bit, it can be 16-bit. So definitely you will improve the quality of the PAM signal if you have more PCM code, the bits with more the PCM code with more bits, or if you have more number of samples, or if you have more number of sample, if the sampling if is done at a faster rate, still you can reproduce better signal. Or if you have resolution, if your step size is very small or your resolution is high, then also the quality of PAM signal can be improved, and therefore quantization error can be reduced. So in the next lecture we will see the types of quantization.